Happy New Year, tensor friends. This is part 3 of the search for the Gaussian curvature tensor. Okay, a quick review of where we've been. So we have the three-dimensional Cartesian space. We're calling this the ambient space. Okay, and we picked a point among anywhere, and we put then a sphere to that point with a constant radius, and that point then is a function of the angle, the theta from the North Pole, and the angle phi from the equator, all right, at a fixed radius. And we said we can put a tangent plane on that spot, right? So we have a tangent plane right at this dot on that the sphere, and we calculated by using the shift tensor that we derived. We calculated the basis vectors in that plane, and then once we had our basis vectors, we could calculate our surface normal, which looked like that. Okay, so with all the calculations we've done, this is where we've gotten. All right, now what I want to do is take the surface, the basis of the vectors, and put them down in the XY planes so they're easier for us to see, because it gets very messy when this is suspended out in space like this. So let's erase the board, and let's go down and put these vectors down in this XY plane, okay? Stop doing that. So there's one of them, two of them. So this is S1, S2. These are not to the magnitude. I just made up a magnitude and put them there. Here's our normal, right? So the normal, the vector, is perpendicular to S1 and S2. S1 and S2 are orthogonal, but their lengths are not, as shown. All right, so what we want to do is just make up a vector. Boom. It's just sticking out. Now this vector is defined as being in the ambient, the space, because it's not in this plane, right? This is the tangent, the plane. In this case, the XY plane is the tangent plane. So this vector is just sticking out here. And so what we can do is form a projection of that vector onto this tangent, the plane, all right? And we would do like that. So we would drop a projection down to this XY, the plane, the tangent plane. Now from the origin to this, we could put a tangent, the vector. All right, so this tangent, this vector is in the tangent plane. So let's get rid of that, the projection. Now we can do the same thing to this. The YZ plane is the normal plane, right? So we have the tangent plane and we have the normal, the plane. So we can do another projection from that orange vector there, A I'm calling it, like that. Now we can define another vector from here to that projection. I'm calling it Q. All right. So now we have these components basically of this vector, but some of the components are in the tangent plane and some of the components are in the ambient, the plane. Now, it's also should be kind of obvious here that vector, this I'm calling this T and I'm calling this Q, that T plus Q is equal to the orange, which is A. You see it changed the color there. I'm adding it and taking it off. All right. So that's really all we need to know to then go on to our document. Okay, like I said, this is the Gaussian curvature tensor part 3. We're wanting to do a transform from the vector in an ambient space to the tangent space. Okay, so here's what we just looked at. So we have a vector in the tangent space. That's this plane. And it has these the basis of vectors that we derived in part one, S alpha, and we also have a projection of this vector onto this plane, the normal plane, right? And it is a component of the normal, and it's basically its magnitude times the normal, right? Is what that is. All right, so here's where we stand. All right, so we just said that. We just said that. All right, and we showed that vector A, this is A, is equal to T plus Q. All right, so we want to rearrange that as this. So we can say that T, now since it's in the tangent, the plane, it can be written as a linear combination of its components and the basis vectors in the tangent to plane, the same way Q can be written as a linear combination of its components and basis vectors in this normal plane. So that's what we're going to do right now. All right. So remember, we want to use Greek, the letters for anything in the tangent, the surface. So we got the T alpha, S alpha. And now the magnitude of Q is basically what the vector is times the normal, right? So I'm just calling the magnitude of Q the little q. I don't know what. Okay. So now we have this basis vector. We would know what it would be in the ambient the space. It'd just be a linear combination of these components and these basis of vectors. So we want those components of A in this space, the tangent space. That's the point of this. All right. So let's rearrange this equation just to say that vector T is equal to A minus the Q. Dot both sides of this with the contravariant basis, the vector S alpha. And you're saying, dude, we haven't done this yet. We didn't do that. You're right. I didn't do that. I should have done it, but I didn't do it. We're going to do it now. So in part one, we derived from using the shift the tensor the covariant basis of vectors. Now we need the contravariant basis vectors. So easiest way in the world to raise or lower a vector component is by using the metric tensor. And we did in part one find the covariant and contravariant metric tensor. So the contravariant metric tensor times that covariant basis of vector will give you the contravariant basis of vector. All right, so we're going to do it right now like this. So we would say, so alpha is 1, and the component of the contravariant basis of vector would be 1, 1, and then alpha is going to be 1 in the first case and 2 in the second case. So it's going to have these components. S2 would have these components. So we know all this stuff here because we did it in part one. So we just go back to part one. We dig all that out. S11 is 1 over a squared. S1 is this. And S12 is 0. So this is gone. All right. So this is what S1 is. Now we can do S2. Well, in S2, S21 is 0, so that's gone. So it's just S22, which is 1 over a squared sine squared the theta, times S2, which we know. Here it is. It had no k component. It was 0. So that's what S2 is. Now, I'm sure you know this. What is the product of a basis vector and its reciprocal, or a covariant basis vector and a contravariant basis vector, or a basis vector and a dual basis vector? Everyone calls them something different. They're all the same thing, right? So let's do it. So I wrote down here, this is S1 up to here. This S, the contravariant one. Here's S covariant one. All right. We do the dot product. We do a little bit of algebra, and we get 1. What's it better be? So this is one way to always check if you're trying to, if you have one basis vector and you want the other one, so you have a covariant, you want a contravariant, the dot product of those two had better be 1 or you've done it wrong. Now, what is S1, S2 as an example, right? So I wrote down here S1, I wrote down S2, You do the algebra and it's 0. This is another, the factor of these, right? So when I is equal to I, this is going to be equal to 1. When I is not equal to, so if this is I and j and they're not equal, you're going to get 0. So these are the two things you can always remember about contravariant and covariant basis of vectors. Anyway, that's a sidetrack, but it was fun. Let's get back on track. Here's what we were doing. So we had this expression, and we had it in terms of its linear combination of its components, and we wanted to dot product both sides of it with the contravariant, the surface basis vectors like this. All right. Now, I think about this for a minute. Back on our drawing, the Q was the vector in the normal, the plane. So it's perpendicular to this S alpha basis of vectors. So its dot product is 0. All right? They're 90 degrees apart. So we can just drop that. We don't need it now. So we're left with this. Now, what we can do now is express these as a linear combination of their components, like we said. And in this case, we chose a contravariant component and a covariant basis vector. We can express A, which is in the, so this is in the tangent space, this is in the ambient space, right? So the same thing. And remember, back in lesson 1, the way we found the definition of this, the shift, the tensor, was it multiplied by a basis vector in the ambient space was giving us the basis vectors in the tangent space. That's how we found it. Okay, so we can put this back in, this expression, and conversely, we can also write the contravariant, the form of this, as this. All we do is flip these indices on here. I have to use a different index because you can't use the same one twice in one equation. Okay, so we wind up with this equation. So right here, I put this, right? And right here, I put this. We're left with this expression. Well, we know what this is right here, right? We just talked about it. This is the delta of the function, the delta alpha beta. So it's equal to 1 if alpha equals beta. It's equal to 0 if alpha is not equal to beta. We know what this is, so this is a covariant basis vector times a contravariant basis vector gives a delta of the function ji. Well, in the language of tensor, the calculus now, these b's get these betas get absorbed, and these j's get absorbed. So we're just left with this. So the components of the tangent base, the components of the vector in the tangent, the space, is equal to the components of that vector A in the ambient space times this shift the tensor. I colored this in red because I got to go back and find it later. Okay? So now let's get back to where we were. So we were working on this, and we found this piece right here. Okay? Now, let's go look at this normal. Okay? So we had this vector A, and we projected it onto Z, which is the normal. And this vector, the projection, and this normal, it forms a right triangle, right? So the cosine of this angle is the adjacent over the hypotenuse, which is the magnitude of Q over the magnitude of A. All right? So we have a piece now, so we can say the cosine theta is equal to, and I'm calling the magnitude of Q little q, over the magnitude of A. So we solve for Q, and we get cosine theta equals Q over, why did I do that twice? I don't know why. Okay, now let's look at it a different way. We also know that the product of this normal, right? So only from here to that red arrow top, that's the normal. So the dot product of this with this vector here, we can define like this. So n hat dot a vector is equal to magnitude of n times the magnitude of a times the cosine of theta. Right, so we can solve for cosine theta again. So here we have two expressions for cosine theta. So we put them equal to each other, and you know that the magnitude of a unit basis vector is 1, right? So that drops out. So we're just left with this. So that Q I was using as the magnitude of A is actually equal to the unit normal times the vector A. So we can put that in also as we can express it as a combination of its components. So we've got now, and this time it was chosen such that you have a covariant component and a contravariant basis vector. Now it's totally legal to do this. I could have chosen here a covariant component and a contravariant, the basis vector. You can do it either way. The vector space and dual vector space, the people will drive you crazy telling you can't. You can express it either way you want. They're equal. All right, now we express this one the same way. So we're expressing these in the ambient space. Do you see these Latin letters? These are both being expressed as that. And we just talked about this. So EI dot EJ is the delta function, IJ, right? And the I's get absorbed. I'm sorry, the J's get absorbed, and we're left with NIAI. So now we've got another expression we put in red because we're going to need it to put back into our original equation, which is this. All right. So now we can plug in that red piece from here, T alpha, and this part for Q. And we've got our equation. So the vector A, which was out of the plane of the tangent, the space, is transformed from the ambient space to the tangent space by this. So it's ambient components times the shift the tensor times the basis of vectors of the tangent the space plus, you got to add this on, the components of the normal the vector in ambient, the components of the vector in ambient, and the unit normal of the vector. Okay, so this is getting kind of long. We're going to stop there and we'll pick up to it next time. Okay, thanks for watching. I'll see you later.